Assalamu alaikum and good morning. I am Dr. Mohammad Nomani Kabir from United International University, Bangladesh. And the co-authors of this paper are Yasser Al-Jinahi, Wael Said, and Ghulam Saleh Ahmed Salem. Now I'm going to present our work on optimal power allocation in downlink multi-carrier NOMA systems. Our work is related to 5G communication system, and 5G is a catalyst for real-time application like autonomous vehicles, remote surgery, and IoT. 5G enables increased connectivity among numerous devices that leads to higher power consumption. And therefore, energy-efficient communication techniques are necessary for sustainable 5G networks. What we are working on is NOMA, which is a key technology for improving spectral and energy efficiency. So now I am trying to define the power domain NOMA. Power domain NOMA uses the same frequency band by allocating different power levels for multiple users. That means it multiplexes the user in the power level, power domain. And one can use successive interference cancellation at the receiver side to decode or demultiplex the signals so that the signal will be useful for the receiver. There is a key challenge in the NOMA, which is the optimal allocation of power among users so that the sum of data rates is maximized and energy efficiency is achieved. This work will refine the theoretical foundation of the optimal power allocation for downlink multi-carrier NOMA system. Now I briefly discuss the system model and key notation, which is given. The key notations are given in table 1, and on the picture on the top right corner, we can see a base station, and we have many user devices, and we have a circular area, which is actually the coverage area of this base station. And within this base station, the user equipment are randomly placed. So these user equipment are grouped into sub-channels, and for each sub-channels, multiple users are multiplexed in the power domain for NOMA system. So here is some of the notation is important to mention. For example, Qn, which is the lower bound of power consumption for channel N. Here we have the R subscript K and N, superscript N, which is the maximal achievable data rate for user K in channel N. H is channel to noise ratio, CNR, for user K in channel N, sub-channel N. And WS is the sub-channel bandwidth, and PKN, which is the allocated power for user K in sub-channel N. One can use Shannon theorem to compute the maximum achievable bit rate using Formula 1. So this maximal achievable bit rate is given in terms of sub-channel bandwidth, WS, PK power, allocated power, and signal to noise ratio, CNR. But here we have one criteria that must be fulfilled, which is the CNR of device 1 must be less than the CNR of device 2, must be less than CNR of device 3, and so on. So that means it has something to do with the distance. The closer the distance is, the higher the CNR ratio, that means channel to noise ratio is. So if this can be criteria is fulfilled, then we can easily find the maximal achievable bit rate for each user. Now we formulate the optimization problem. That is the actual problem where we want to maximize the data rate under power constraint. So 2A provides the maximal data rate. That means we want to maximize the data rate for all the users in all the sub-channel. For P, that means we want to calculate the power value, allocated power. So based on that, we maximize this one. And then we have 3 constraints. The first one is all the power in all sub-channel must be less than the allowable power for a base station. And the second one constraint is all the power in a sub-channel must be less than the allowable power for that sub-channel. And the power for each user must be more than 0, so must be positive. So actually this problem can be solved numerically, but our goal is to find the solution of this optimization problem in a closed form. So how does it work? We use the Shannon formula to formulate such a proposition, and in this proposition we can view that the minimum power requirement for a subchannel, which is Qn, is given in terms of beta and the H, which is CNR, channel to noise ratio. So this beta is again given in terms of WS and R. That means the subchannel bandwidth and also the bit rate, data rate. So ultimately, this part, minimum power requirement, is given in terms of WS, R, and H. So there is another proposition that tells us that minimum power for a device, for a user equipment, is given by this formula. That means the P, the power, allocated power for each device, is given in terms of AN, A, and H. A is again given in terms of beta. So beta is again given in terms of W, WS, and R. So that means the power ultimately is given in terms of data rate, the subchannel bandwidth, and as well as the channel to noise ratio. Now we made some program in MATLAB and run this program using the setup which is given here. So the total number of user is 17, and total number of channel is 4. And for 4th channel, we have 5, 4, 4, 4, this number of users we have. So this is given in this picture. So we can see that we have 4 subchannel. Each subchannel has different number of users. Actually, the first one has 4, and the others will have 4 user equipment or users for each subchannel. And these 17 devices are randomly placed within the 20 to 500 meter distance from the base station, and we have a circular area that covers the coverage area of that base station. And we have some more information like total bandwidth and minimal data rate. Total bandwidth is 5, so the subchannel bandwidth will be 5 divided by 4, that is 1.25 megahertz. And we have some more information, for example, distance dependent path loss, which is given by this formula. And we have also a small scale fading, which is taken as the Rayleigh flat fading. And we have also additive white Gaussian noise, and that value, the density value, is minus 174 decibel meter per hertz. So these all the information are used for MATLAB simulation, and we get the result. First result is the H value, that means CNR, channel to noise ratio, And we can see that channel 2, we have 4 channel, and first sub-channel we have 5 users, and the others are having 4 channel, 4 users each. And the first user has actually the farthest from the base station, and therefore the H value is the lowest, and the last user is the closest to the base station, and the H value is the highest. And same follows for all other sub-channel. So we now calculate the corresponding power for each user, and one can see that the opposite of the H value. So the first user requires higher level of power because it is farthest from the base station, and the closest one requires the low level of energy, low power. So it is the closest, the fifth user is the closest to the base station. Same follows for the other channel. So here, the finding is that we refine the theoretical proposition for optimal power allocation in downlink multivariate NOMA. And this model can be used for accurate analysis for 5G NOMA in 5G network. And we have also demonstrated that the model from the two propositions comply with each other. That means the result comply with each other. Future research can be concentrated on the imperfect successive interference cancellation. And also we can have some realistic channel estimation error and feedback delay to get more accurate model. And we can also extend this model to the massive MIMO, NOMA hybrid architecture.